So still looking at tangents and normals, but this time taking a Cartesian approach rather than using the parametrics. So the tangents, so once again, there's our parabola, x squared equals 4ay, but this time I'm just going to give the point an x value and a y value rather than the Cartesian, so x1, y1 if you like. So there's our tangent. So we've still got to do the same process. I'm still going to have to differentiate and sub in the x value to find the slope. So it'll be x1 on 2a. So I know the slope of the tangent. Sub it into the point slope formula and rearrange. Now, when I look at this, I can do something quite clever. See the x1 squared on the right hand side there? I can change that because I know x1, y1 is a point on the parabola. So I could rewrite x1 squared as 4a y1. And something quite nice happens. So I now have it as 4a y1, rearrange it, and we write it in this form. And it looks a little bit strange, but there is some logic behind it. See, x1 equals 2ay plus y1. And the reason we put it that way is to highlight that's the equation of the parabola. If you look at it, the parabola is x squared equals 4ay. I've got x times x1, a point on the parabola. Well, x times x is x squared. Look at the right hand side. I've got 2a, y plus y1, which is the point on there, but y plus y is 2y. 2a times 2y is 4ay. And so there's this beautiful pattern that the equation of the parabola mimics the equation of the tangent and vice versa. And that happens with all the conics actually. And so when we look at later on ellipses and hyperbolas and things like that, we'll see the same sort of thing happens. And that, I guess, is one of the advantages of using Cartesian coordinates, because we know, well, the tangent will mimic the equation of the parabola itself. The normal, not quite as nice, but let's see what happens there. So there's our random point. This time we're finding the normal. So the slope of the tangent was x1 on 2a. So the normal will be minus 2a on x1. Put that into the point slope formula. x1y minus x1y1 is minus 2ax plus 2ax1. Now, we tend to write it this way. So basically on the left-hand side, I've got all the things involving x and y, and the right-hand side is just the constant values. But again, there's a little bit of a pattern there then, because you can see that in this case, the left-hand side sort of mimics the right-hand side of the equation. So you've got 2ax on the left-hand side, but on the right-hand side it's 2ax1. And on the left-hand side we have x1y, whereas on the right-hand side it's x1y1. So there is a little bit of a pattern there for the normal. Now, if I remember correctly, yes, those ones are given. Mind you, I noticed on the reference sheet, they just leave the normal as y minus y1 is minus 2a on x1, x1 is x1. They just leave it like that for some, so it's not quite complete. But it is there on the reference sheet anyway. If when you're in a test and you go, oh, hang on, mental blank, they've only asked me to write it down, so I don't want to derive it. You've got the reference sheet you can refer to and do it that way. All right, well, one of the ideas, lines cutting, touching, or missing a parabola altogether, and we use a very common idea that comes up a lot, certainly when we're dealing with parabolas, which are, of course, quadratics. We go back to some of our quadratic theory. There's our parabola. So a line might cut it in two places. It might be a tangent, so it might just touch it, or, of course, it could miss it altogether. So let's give the equation of the line, y equals mx plus b, our standard equation for a line. Now we know they're going to meet. Well, if we wanted to find out, we'd solve them simultaneously. So I'll say x squared equals 4a, but instead of saying 4ay, I'll say 4a mx plus b. And we create a quadratic equation. So making it look like a quadratic, there it is. X is the pronumeral. And of course m is the slope of the line, a is our focal length, b is the y-intercept there. Well, Now we go back to our quadratic idea and the discriminant, because the discriminant tells us how many solutions. So if it cuts it, it must have two solutions. So we know the discriminant is greater than 0. So we don't actually have to solve the equation to find the slope of the line. I can just look at the discriminant. And it will touch or be a tangent when the discriminant equals 0. Now that's quite a common idea. We saw that, I think, in our examples before when we were saying when does a line touch a circle? Same sort of idea. We created a quadratic and said, well, we know the discriminant of that must equal 0. And of course it'll miss it all together when the discriminant is less than 0. So b squared minus 4ac, let's sub in. So b is minus 4am. A is 1, C is minus 4AB. Tidying that up and factorising, I've got 16A outside of AM squared plus B. Now, because we're dealing with 0 here, the 16A is irrelevant, because we know that's a constant value. We know that's not going to equal 0. So it must be the other factor that's going to be the 0. So now I can simply say, well, hang on, that means there must be two solutions when just that am squared plus b part is positive. The idea we see a lot more often, of course, is the tangent one, so it'll equal 0, am squared plus b will equal 0, and that's how we can find the slope. As I say, very common idea, we use that one. And of course miss it all together when am squared plus b, whatever that is less than 0. So it's tying in our quadratic theory with our parabola theory. So let's do an example of that. In fact, it is the exact same example I did yesterday, but I did it with parametrics yesterday. So now we're going to use this Cartesian idea. Find the equation of the two tangents. So I'll be using the idea the discriminant is equal to 0. Okay. So I'll say, well, the tangent I know will be in the form y equals mx plus b. Okay. So therefore, 2 will equal 3m plus b, because I know that point, where we're saying the tangent passes through the point, must satisfy the equation of the line. So I'll just make b the subject there. So b is 2 minus 3m. Okay. Now I know the equations of the tangent. I don't need to worry about b. All I now need to find is m. Because I can say, well, it's going to be mx plus 2 minus 3m, whatever that turns out to be. Okay. Well, we also know the parabola is x squared equals 4y. So if I solve those simultaneously, so substitute in the mx plus 2 minus 3m for y, create my quadratic. So there's my quadratic. We know the line is a tangent, so therefore we know the discriminant has to equal 0. Let's find our discriminant. So b squared minus 4ac is equal to 0. And we should have a common factor that comes out there. 16 looks like the common factor, doesn't it? Now, you might recall the equation from yesterday. No coincidence, we've ended up with the same equation to solve. m minus 1, m minus 2 is equal to 0. The difference yesterday, of course, is that was the equation to find the value of the parameter. This time it's to find the slope of the tangent. But remember yesterday we also proved that for our standard parabola, the slope of the tangent is the parameter. So we did it one way with parametrics, got the answer. Doing it here with Cartesian coordinates, we get the answer. M is 1 or 2. So subbing back in, there's the same answers as yesterday. Y equals x minus 1, y equals 2x minus 4. So two different approaches depending on if they don't tie your hands, of course. Sometimes with questions they can tie your hands and force you to do it one way. But if they don't, you have a choice. I might use parametrics to solve this, or I might use Cartesian coordinates to solve this. Okay.